make sure we understand the basic exact sequence. I wrote it on the board, but I'll write it again. You have the standard injection of the constant functions into the smooth functions. And then you have the associated smooth function to a vector field, and what you get here are vector fields which are for sure at least local Hamiltonian. And so this mapping is H of F is defined by taking df. So H of F is equal to X. I use X sub F, where I'm just repeating everything, but I don't think it hurts. df is equal to omega of x f, so the contraction of x with omega. And this is the mapping that takes a function to the associated Hamiltonian field, and we know that you land in what I call the local Hamiltonian fields. These are the fields that are the local isometries of the symplectic form. That's where you land. And not all of those are in the image. So you need another mapping here, maybe I call it theorem, which goes to the first theorem cohomology. And in fact, it's surjective, you can show. So we have a long exact sequence here. And this mapping theorem of xf is the theorem class of omega contracted with xf. It may or not be, it's close, but it may or not be exact. That's it. That's a beautiful summary of what we know. And the tool here to prove this is Cartan's formula, which is an extremely useful tool in general, which tells you that the lead derivative of anything is the anti-commutator with the d operator. And that's easy to prove, and I just don't want to take 15 minutes proving it here. I will put it, I have put it in the notes. I've written the proof, and you can take a look at it. Okay. So that summarizes what's going on for this Hamiltonian mechanics. And in coordinates Q, P coordinates, which we also have by Darboux, where the Hamilton, the symplectic structure is just dp, dq, dp. Then let me use the letter H, H, XH can be written explicitly as minus dH, dp, dq plus dH, dq, dp. So the ODE that you're trying to solve in these coordinates is Q point equals minus dH dP, and P point equals dH dQ. And this is the cotangent version of geodesic flow. May or not be a global flow, depending on many things.
I think that's a co-vector field, right? That.
I made a mistake or something.
Isn't that a co-vector field?
Hmm?
That x-axis looks like.
This?
Yes.
That's wrong?
Well, it's co-vector field, right?
Huh?
The way you write it there.
It's not right?
I need to write dq.
This is,
It's co-vector field as you write it there. It's not vector.
it's the same as this.
I just mean that this is co-vector field and not the vector field.
Can you write on the board what you're saying here?
I mean, this is co-vector field, not vector field. What you just
Oh, it's a covector field. Yes, it's, that's right. I've written it as a covector field. I'm terribly sorry. This would have been, no, that's funny. That's funny that I did that, but okay. It's not funny. It's absolutely false. Thank you very much. Okay. There's so many letters here that I'm bound to make a mistake, so it's good that you watch. Okay, now you're happy. Okay, so that's the situation. And it's very difficult to find explicit formulas for the geodesic. So what we do is we look for invariants of the flow. So we look for invariance of the flow, whatever that means, of geodesic flow. And then one kind of invariant, an example of an invariant, is a function, say a function f, so a function on the manifold with the, so let's use the notation here, xh of this function equal to 0. Right, so we're differentiating the function with the vector field. So that means if you're looking at a level surface, say, which is smooth, the generic level surface f, which is smooth, f equals a constant. Here's a level surface, taking a smooth one, and it means that the flow of this is the flow is inside the level surface. Geodesic flow, the function is annihilated if and only if the geodesic flow is contained in the level surface. Means if the derivative kills it, then it means it stays inside there. Okay? Yes?
So what is the difference between the geodesic and the geodesic flow?
Okay, very good. It's just, first of all, it's just a matter of language, so, but it's very good that you asked that question. So her question, what is the difference between geodesic and geodesic flow? When we use the word geodesic flow, it means the orbits, let me be very precise. It means the local one parameter group action is defined by this ordinary differential equation. Okay? So it's really, and maybe some people, when they say the word flow, they mean one orbit. But I mean the full action, the full local one parameter group action. That's what I would call geodesic flow. And a geodesic is then one of the orbits. Okay? And it's not so clear. Maybe the geodesics are not global, right? I mean, maybe it's not a... So what I mean is, at least locally, it's a solution to this ODE. Of the Lagrange equation. So notation, we use the classical notation here. We say that F is a constant of motion of this dynamical system. Okay, it's a smooth dynamical system, it is ODE, and we say that F is a constant of motion in this dynamical system. F does not change. Okay? Now, let me introduce very useful notation coming from, again, from physics. Coming from the study of mechanics. I don't know the history of this, but I'm going to define an operator, F, operating as an operator on functions. So an operator on functions. So there's an operation of F on functions. So the function goes in here. On smooth functions. By this thing, and I'm going to put in the right sign here. I'm going to put in the correct sign, it's minus. There's always some sign convention that it makes a difference. This is correct. I thought about this. So this is the correct sign to make all the signs come out nicely. Somehow it also makes a difference. I don't know. Anyway, so this is an operator. So let me just emphasize that this is called the Poisson bracket. This Poisson bracket of F on G is just you take the derivative of F of the vector field, XF on G. That's just the way the function F is acting as an operator on other functions. It's a good way to think. You're coming close to seeing functions operate as some sort of operators, right? You're starting to think in quantum mechanical terms. Right? So that's what it is. And you check with all of this little notation that's going on that the operation of F on G is omega, and it should be backwards here actually because of that minus sign, but I like the minus sign for other reasons, of Fg. Okay. You just check that. It's formula. Maybe you have to use Cartan's formula again. Maybe not. It's just purely formula. Okay. And now you study what it means, meaning d omega equals 0. You write down what it means, that d omega equals 0. You must agree that d omega is the 3 form. Whatever it is, it's a 3 form. right? And so you can imagine that it has some meaning here, and what the meaning is this. It is that this is it's equivalent to what we call the Jacobi identity. Which is f, this is acting as a derivation in this way, so FGH equals FGH plus GFH. Now you see, I'm sorry I left out a bracket here. When people see this for the first time, they think it's completely insane. But if you think of f acting as a derivation on this product here, it's acting as a derivative on this product, it's f acting on the first factor times h, plus f acting on the second factor with g on the first. So it's exactly the derivation rule. Jacobi identity is precisely a derivation rule. So it means, remarkably, that the C infinity functions, you can check it, equipped with this so-called Poisson structure, is a Lie algebra. I know you have had some experience with Lie algebras, so you know what these things are. The key thing is to have the Jacobi identity, and that's it. Okay? It's a Lie algebra. Right? It's the same type of Lie algebra as the various functions are. So this, as the various vector fields, spaces of vector fields. This is a Lie algebra. Yeah? It's wonderful. And there's something even better. You check that FGH, see, you've got a lot of structure going on. You have multiplication by Poisson here, but you have also multiplication by the usual functions. You check what that is. This is, I don't know how you like to write it, is GFH plus HFG. This functions commute, so I can write that in a sloppy way. So this is more than just the Jacobi identity. And this is this identity plus this derivation rule here. And these things together are saying that C infinity functions equipped with bracket is a Poisson algebra. That's just the words that you hear, and all of this comes from the notation in physics. Okay? These are good things there. So this Poisson bracket has all of these good properties. And what you're thinking of, as I said again, you would just want to think of F acting on G by the vector field. Okay, I choose a sign, but that's not too important. F acts on G that way. And it's not, yes, ma'am.
Is the Poisson bracket commutative?
Is it what?
Commutative. No, right?
You see, it's a very good question.
It's not the solution.
You would hope, if it's a Lie algebra, it's anti-commutative. And don't forget its definition, and don't forget this is a two-form, and so it is anti-commutative. So a good question. It's the condition of a Lie algebra that it's anti-commutative. Right. So these are the things that are hanging around in physics, and you start with a Poisson algebra and you want to quantize it somehow to an operator algebra of, say, bounded linear operators on some Hilbert space or something like this, and you find out, and that's a basic fact, you cannot do it because you cannot quantize the full C infinity functions. We just said you cannot quantize the full space of C infinity functions. Right. You can't do it. So you need to cut down on the size of your functions. So you're considering that you want to quantize. Quantization means you send a function to an operator. But it should obey it should be a bracket obeying mapping. This is a key thing that Dirac insisted on. And you can't do it with the full function algebra, so you cut down on the size of this thing using what Dirac called polarization. And this is very close to considering things that are holomorphic and anti-holomorphic, so it's near to my heart. It's very, very interesting mathematics. You no longer consider all functions. Of course not, there's too many. And you consider functions of z and functions of z bar. Things like that. Okay, so that's a little bit of the blah blah, just so you see some notations coming from physics. The Poisson algebra structure it's defined immediately by thinking of this stuff. And now, what is the meaning of f g equals 0? What does that mean? And let's look at what it means. Well, I said you should say that you should regard f as an operator on g. So this is in particular the meaning, it's symmetric or anti-symmetric as Maria is pointing out. This is the meaning that the Hamiltonian field associated to f annihilates g. This is the meaning, well, it's the same thing. This is the statement that, okay, this says, the statement is that G commutes, well, this is a statement, well, let's write this here. I'm very happy with your remark about commuting and anti-commuting. This says this is 0, it means that it commutes, f and g commute. Right? Since it's anti-commutative, this means that f and g commute. So this is in algebra, this means f and g commute. This is 0. And that means that g is a constant of motion for the flow of Sx. Right? That's what it means. Constant of motion. Okay. Now let me change the notation a little bit. Start with a Hamiltonian system. A Hamiltonian system. i.e. we're starting with what we call a Hamiltonian, I'll just call it, let's call it with H for Hamiltonian. Unless you were stupid, and you are not, the first thing you look at then is the centralizer of H in the Poisson B algebra of the C infinity function. This is a word. Just means that everything that commutes with H. It's called the central. The word auf Deutsch sagt man Centralizer. So Z is because this whole theory starts in Germany. So some people write C for English, but I always write Z. It means everything that commutes with H. Yeah? These are the constants of motion. These are all of them. These are all constants of motion for H. So this is a space of all constants of motion of H. Of XA. Now your goal would be to have as many as possible. Right? You would have one, that's some manifold that's stable, all these stable manifolds. You see them with one. Then you have another one. which is independent, and they cut, and now you have, instead of codimension 1, you have codimension 2, codimension 3, codimension 4, if you're lucky. Okay? You would be lucky. Okay? By the way, Ayman talked about homework to me on an email just now. I think I don't worry if you turn in homework a week later or something like this. I don't worry. I just want you to think about things and send it to me when you have a chance to think. Think slowly and ask good questions. So far, I'm very happy. And if you see what I mean, no big thing about because I just want to look at each thing you send to me, a file, and I will make my remarks, and that's it. And you get a 100% grade if you try to understand something. And if you try, I'm sure you will understand something. So, I don't know why this is from this morning, I think. Okay. So, the goal would be that the centralizer of H is as big as possible. Right? Yeah?
So, since we're considering the C-infinity functions, do we regard H in this context as a C-infinity function?
You know, I'm having such trouble understanding. So say it.
So do we regard H in this context as being a C-infinity function?
Yes, everything's C infinity.
So it's just a function?
Function. Everything's C, yes. Yes, H is a function, and we're looking at all functions which commute with H. And that means that F is a constant of motion of the Hamiltonian flow of H. Right? So the goal, so step 1, H, this is devoted to Maria, equals 0. She pointed out that I should worry about commutativity or not, but since it's anti-commutative, is 0. So it means that H is a constant of motion for the Hamiltonian flow XH. That's an example. That sounds trivial, but I will formulate it in another way, in the way physics people like this. So as an example, so with the symplectic manifold M, M equal the cotangent bundle, so the cotangent bundle of M in the standard form, and H defined to be the dual metric, the dual norm. G, well, let me just call it norm squared of the dual of the metric. Do you understand what I'm talking about here? If you have a metric on a vector space, then you have the dual metric on the dual space. And it's more or less the inverse metric, up to constants by, you have to have some constants here, maybe with Legendre transformation, but maybe 1/2. That's the 1/2 that may arise in physics, I'm not sure. This is more or less the inverse matrix, is inverse matrix. So this you have this dual norm.
So,
Yes.
using what? The metric or the form? Symplectic form?
Let's start, I don't know where your question is, we're going to start from scratch. If we do differential geometry, we are on the tangent bundle,
Yeah,
and we have a metric.
right. And the metric has...
The metric is Gij, is a symmetric positive definite matrix in coordinates.
Mhm.
Okay, we're okay on that level.
Yes.
Now we go to the cotangent bundle. We have dualized everything.
Yes.
So we have the dual norm. So if you have an isomorphism defined by the metric,
Okay. So
that's the only thing we have.
Mm.
Or it will be Legendre transformation also, it doesn't matter, okay?
Mhm.
That's where the 1/2 actually appears because of Legendre transformation. Okay, so what it is the inverse matrix,
Mhm.
okay?
Okay.
So that's the obvious norm on the cotangent bundle. The dual inner product. Okay. This is the Hamiltonian. You look, and this is the Hamiltonian. So it means that this thing is invariant. It is a constant of motion. Now you can prove this by computation, but this follows immediately. Okay. Now, I drew this picture before, but let me draw it again because just to keep sure, to make sure you're. Now this here's M, and here's a cotangent bundle. And here are these various, and here are the level surfaces look like this. Various level surfaces. This is the level surface of the norm, so h equals a constant, norm squared equal a constant. Okay? And it says that the level surface is invariant. It means it's invariant by the local group action. It means, I mean, you believe this, that it should be invariant. The metric should be invariant, so the dual metric on the Hamiltonian should be invariant. So this means that it looks something like this. These are not self-intersections. It's a geodesic flow. No, it looks something like that. You got the picture? You have the H level surface in the, yes, the unit, you were asking about sphere bundles. I mean, this is then a sphere bundle over the base space, right? Because each thing is just the unit sphere or the, well, maybe I didn't take the unit constant, H equals 1, right? This would be a sphere bundle. So you have the sphere bundle. Let me just maybe put this in here. This thing would be, if this manifold is n-dimensional, then the fiber is n-dimensional. This would be n minus 1-dimensional sphere. So we're getting back to all these questions. This is geodesic flow on this sphere bundle, and when you push it down, which is what everybody cares about, you care about the geodesics downstairs and what they're looking like, terrible things happen. They will intersect, self-intersection, and so on. There are all sorts of interesting phenomena when you push it down. Okay? But when you're upstairs in geodesic flow, when somebody says geodesic flow, that's what it means. This means this is the geodesic flow here. Okay? So the important dynamics of the Hamiltonian mechanics are going on in the unit sphere bundle, or some other sphere bundle of radius k. It doesn't matter. I mean, what would you change? Everything okay? Yeah.
Well, it's a stupid question, but why is h a constant of motion for the vector field of h? So why is the h 0?
Why is what?
So why is h 0?
Why is h?
The sum bracket.
Yeah, the
Why is
sum
h comma h 0? That's the question.
Oh! Because you made me say that. It's anti-commutative. So h equals minus hh. I commute.
Yes. So why do they commute?
Why doesn't it commute? Because it's a two form. Look at the definition. It's a two form. There it is, way up there at the top. And a two form is alternating.
So judging by that, I can put in there f, and then would be commutative, and that's it?
F is also 0. Anything is 0.
Okay.
It's anything is 0. It's all, that's a fact about two forms. I mean, it's a dumb thing. It's completely dumb. Right? But by the way, H is quite often referred to energy, and this theorem here in the formulation probably of neutral is called conservation of energy. So this theorem is called conservation. The geodesic flow or anything like this, Hamiltonian system like this, satisfies conservation of energy. That's all there is in all the big derivations that you've seen. This is it. This is the only thing going on. Conservation of energy. It's the fact that HH is 0. And the reason HH is 0 is HH is equal to minus HH. And it's because the two form is alternating. Yeah? It's trivial. You just have to formulate it. Okay? So this is conservation of energy. And this morning we had the Lie derivative of x of omega equals 0. That's of course saying that the image is in the local Hamiltonian flows. And this is conservation of area. Well, let me put the quotes on the word area because here we're thinking of the symplectic 2 form as defining area. Okay. So we have already seen two things that are invariant. Okay? Okay. So now I'm going to explain something that in geodesic flow almost never happens. But it's important for you to know when you are talking with your physics friends and when physics friends are talking to mathematics friends and they have some blah blah going on and you want to understand what this blah blah means. The absolute optimal, you have to think about this for a while. The optimal situation that you can hope for, the best you can hope for, is you have a bunch of Hamiltonians so here M is a two-n dimensional manifold. And they are analytically independent. And maybe you don't know that word. Analytically independent means that the differentials are independent. At all points of being considered. So I'm trying to say you have really as many constants of motion as you could hope for. Okay. Please let us think together about this. You have one constant of motion, you have its hypersurface. The geodesic flow, let us say you think of this first one as being your Hamiltonian of consideration. So you have its level surface, you see it? And then these other things commute with it. So they are constants of motion. So their level surface is cut, right? So this flow has to be tangent to this manifold and tangent to this manifold. So it has to be tangent to the intersection. So that's sensational, right? Because you cut down on the size of the dynamics. Yes, this is codimension 1, now it's codimension 2. Now it's independent, a third function which is independent. It cuts. This independence condition is a statement that you really cut and you get smooth manifolds and you go down, 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 down. It says that the best thing here is H1 equal to C1 and so on. H n equals Cn are all constants of motion, and therefore, if you take the intersection of these sets, this intersection of these sets are invariant. If you think about it for a while, this is about the best you could do. You see what I've said? Do I need to say it again? They're independent, so you cut, 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 cut. Each time the flow that you're talking about is tangent to the thing, because it's a constant of motion. So that means it's tangent to the intersection. The intersection is codimension n. Okay? You will see that this intersection is Lagrangian in the context I'm going to talk about, but okay, in a minute. So this is an optimal situation, and this is called a completely integrable system. If they all commute. So they commute with each other. They're all constants of motion of each other. This is the optimal thing. This is called completely integrable system. Okay? You can imagine how wonderful that is. To have such a system. Okay? Yes?
And is the union of all of them the entire system?
It's great, I have to ask you every time, and then it's great, you can repeat, and then I can understand it.
The intersection is invariant. What about the union of all of them?
Well,
Is
the
it
union
system?
is stupidly invariant, but the union is not very useful. I mean, why not? The union is this, union that, union this, union that's a terrible thing.
Isn't it the entire thing?
Hmm?
Isn't it the
No, it's a union of n codimension 1 manifolds. I mean, it's like the union of n. You take in R3, take planes of dimension 2, they're codimension 1. You take a bunch of those planes, you see that. I mean, you get the union of these planes. But the key is the intersection. And you cut down, when you take the intersection, you're cutting each time, so you're losing dimension. And this is, if you think about it for a while, you will see this is about the best you can do if all these things commute with each other, and they're independent and so on. And you can check if the set where H1 equals C1, and the set which we're talking about, this intersection set, if this set is compact, that's a good condition. So if the ambient manifold is compact, for example, this is smooth, then it is a torus. You can check it. It's not hard. This is called a theorem of Liouville, but you can check it as a homework exercise if you want. It's a torus. It's a torus. And the flow is in the obvious coordinates. Is linear. Now, in kindergarten, in school, you talked about a torus being a parallelogram in 2 dimensions, right? And then you drew a line which maybe had an irrational slope or a rational slope, depending on it, right? That is a flow. That is a geodesic flow, right? That's exactly what that is, right? That line is geodesic flow, and that's linear geodesic flow. Okay, on the torus. If you have enough constants of motion in this sense, then the intersection of these level sets is invariant, and the flow on that torus is linear. You cannot do any better. You cannot do any better. That's wonderful. So, let me just tell you to tell you some serious mathematics instead of this introductory mathematics. This is also serious, but it's just introductory. In an example, suppose all of these multi-level surfaces are indeed compact. Okay? So I talk about one of them here, but if you're doing mathematics, you should never talk about one thing. You should talk about when the parameters move, right? So you have, here I'll draw this in as one torus. You have for some, I'll make a parameter space here. You have for some parameter of some constants here, C. This is some parameter space here. This is a torus which depends on C. And you have a nearby thing, another torus, which depends on maybe C hat. In other words, you have a family of tori which is moving, parameterized in a beautiful way. Okay. That's the optimal thing. That is the optimal completely integrable system. Okay? Okay. And now, to give you a feeling for the history of this subject, there was a very famous theorem, which is called Arnold-Liouville theorem. That what this is more or less the cotangent bundle of the base. So I'll call this manifold M that parameterizes this. This is more or less the cotangent bundle of the base. This is more or less the cotangent bundle of the base. Except, of course, these fibers are all linear spaces. So if this fiber over the point C is the cotangent space of the fiber C, and this torus over the fiber C is the cotangent space over C, modulo a lattice. You know what a torus is. It's a vector space modulo a lattice which depends on C. Modulo a lattice which depends on C. As you move in the cotangent bundle, you have moving lattices that give you this beautiful thing, and the lattices are computable. This is one of the most beautiful theorems you can think of, right? If you have an optimal situation, conceptually, when you have as many constants of motion as possible, that means they commute with each other, and you have as many as possible, namely n of them, and they're independent and smooth, then you have this theorem of Arnold-Liouville. Okay? Very interesting. Very interesting. Very interesting. Now, if you're a good mathematician and a good physicist and a good scientist, you say, when does that happen? Right? And the answer is never. It is only a good mathematical situation. Yes? So, you have this good mathematical situation where the flow is linear on each torus. The lattice is changing. Sometimes you get closed orbits, sometimes you have this, that, and the other. You have this beautiful mathematical situation. Arnold-Liouville didn't prove much anything at all. It's a theorem of Arnold. This just comes from the cotangent bundle with moving quotients and tori. It's incredibly beautiful. You ask Arnold if that ever happens, and he will tell you, no! No! There is no such thing as the exact solution to a physical problem, or a geodesic flow, or anything like that. It's too complicated. It never happens. So, fortunately, Arnold, of course, was in Moscow. And in Moscow, the leading figure of all of that mathematics starts with the letter K, and make it very big. It's Kolmogorov. Everything that Kolmogorov did was really serious. Probability theory, everything, dynamical system, information theory, everything. It's unbelievable. And Arnold was a student of Kolmogorov, and they talked together, and they asked the question, is this situation stable? This is a very interesting question. Let me tell you a little story. We had a great honor at my German university to give, in particular, honorary doctor's degree to Jürgen Moser, who is interested in these kind of things. I've mentioned his name already. And I made big propaganda in the newspaper that these wonderful mathematicians were coming, and we were honoring them, and it was a great honor for us, and so on, you can imagine. So the journalists come. We were sitting on it, I remember vividly, with the table at nighttime with Moser drinking a little bit, fortunately. And the journalist said, what do you do for mathematics? He said, I'm interested in stability. And she said, well, what does it mean, stability? And he said, well, in mathematics, I'm just quoting him now because what he says is great. In mathematics, we have idealized things that never happen. Yeah? For example, what you have in the back of your mind is this idealized dynamical system with all these invariant toris and linearized flow. It could not be better. And it never happens in nature. And he said, for example, you have completely integrable systems. For example, the two-body problem, the moon and sun and so on. These things, there are certain systems that are completely integrable if you write them down theoretically in mathematics. But in nature, what does it mean? And he said, you have to understand what it means, stability. Right? It means you change everything by a little bit, right? And hope that the dynamics remains more or less the same, right? You change everything in sight by everything, a little bit. Okay, you change the manifold by a little bit, you change the symplectic structure a little bit, you change the Hamiltonian a little bit, yeah? And you control what a little bit means in a good way. And then you ask if the dynamic stays the same, or close to the same. Yeah? This is the right question here, right? This theorem of Arnold is a theorem that I can prove very easily. If I had known that you should prove this theorem, I can sit down and prove it. Arnold would probably prove it in a day, I'd prove it in 2 days. Okay? This theorem. It's not hard. But the questions of whether this is a stable situation or not is non-trivial. Right? So he explained what does it mean, stable, and you perturb the values of whatever you're doing, and then she says, is the universe stable? He's saying it's a wonderful question. And then he said, well, in the sense of Hamiltonian systems, you have effectively the tangent bundle or cotangent bundle, and you have particles moving all over the place. And you have, each particle has a position in a non-relativistic situation, coordinatized by 3 variables, and a velocity, or a momentum depending on your point of view. This is what he says. So each particle moving around in the universe has 6 numbers associated to understand where it is, right? We're in the tangent bundle, the cotangent bundle, so that means 6 numbers, right? And now we have, for example, the 3-body problem. How many do we, I mean, it gets very big just by considering planets. And so he tried to explain It's extremely difficult to prove stability of the solar system, anything like that, for such a huge system. These problems are very, very difficult. But Kolmogorov and Arnold prove not stability, but close to a good thing. If you perturb this situation in the way I mentioned, you will still have some, and this sum is made precise, some invariant tori. Isn't that interesting? It says you cannot ask for closed orbits or things like this, but you can have the next best thing, invariant tori, and you will have some. You will lose a lot of these, but not this whole family, but you will still have some invariant tori. Now, they prove that the way Poincaré proved things using series methods, so assuming that all manifolds at hand and everything at hand is real analytic. This means it's almost like a formal solution to the problem. You know, with real analytic you make coefficient comparison and so on with power series and so on. But in fact they proved with convergence, so it was a correct theorem. But Moser came, and Moser wanted to make an improvement of this theory and proof for smooth functions. And he invented a huge new point of view just to improve this to smooth functions, which is very, very important anyway. And introduced a lot of new techniques into symplectic geometry to prove the so-called CAM theorem, K-A-M. We call it CAM theory. It means Kolmogorov, Arnold, Moser. Those are the three of the greatest names in mathematics of the 20th century. Yeah? It's called CAM theory. It states that if you take a completely integrable system written down in Arnold way, like this, and you perturb the numbers, you will still have, in a very quantitative way, a certain number of invariant tori after that. This is called CAM. This is a beautiful theorem. And of course, geodesic flow is essentially never like that, but the whole setup is like that. Okay? Okay, thank you for your patience. I will continue lecturing, but I just wanted to get that off my chest. It's, oh, by the way, to give you the time frame of when this is in the 1950s, 60s, something like that. You can look it up. Okay. And of course, Moser's methods that he developed because of this are very, very useful and generated a huge amount of mathematics. Well, it's only been an hour, but I think it's a very nice place to stop, so let's have a break now until 15-minute break is okay? Okay? Thank you.